So now we move into permutations and the permutation principle. They're actually not that different from arrangements and the factorial principle. The difference is when we think about arrangements, we are actually taking all of the items, so arrangements, all n items are placed in some order. So a lineup of different people, of books, whatever. A permutation, on the other hand, is just some selection of R items from a collection of N in an arrangement itself. So for instance, instead of talking about, as an example, let's say there are 23 neighborhoods that are being selected for a cluster sample. Out of those, we're only picking 5 of them in order. So if we're talking about the greater Sacramento area, right? So they might need to be in order because somebody's going to visit them or something needs to be done geographically. So just as an example, we'll say maybe it's Arden, Carmichael, Fair Oaks, Orangevale, and then Folsom. Right, so in that order, if we swapped the order of these two, for instance, then it's a different permutation. So this is an example of a permutation. The thing about permutations is they're actually very helpful because sometimes we don't want to select all of the things at once. So here's another example. From a 52 card deck, we select a hand of 5 cards. So again, we're not selecting all of them, but the order may matter, in which we say, okay, well, I'm picking them in order, and let's say I get I'll get a 3 of clubs, 3 of diamonds, maybe a king of clubs, king of hearts, and ace of clubs. So these are again 5 cards, but again, if the order and somehow is switched, so these two or any combination of them, then we are talking about something different. It would be a different permutation. Why this is so important is because to calculate the number of possible permutations, we use the permutation principle. So, permutation principle, which comes out of combinatorics, tells us that the number of different permutations when n items are available and R are selected without replacement, of course, then that is this number, which we denote sometimes as P of N and R, and it's literally going to be this calculation. So n factorial divided by n minus r factorial, which is the same as n times n minus 1 times dot, 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 all the way up until n minus r plus 1. So why does this work? Let's think about it concretely. So example, let's say I have 20 students in a class, and I want to select 4 for a group in order. So again, we're talking about random selection, right? Random selection without replacement. So what, if we think about it in terms of our previous ideas, we have essentially just 4 spots, right? We're only looking at 4. And for the first spot, we have 20 possibilities, so there's 20 possible students. And for the next spot, now we only have 19 left to choose from, and then 18 to choose from, and then 17 to choose from. So that is 20 times 19 times 18 times 17. 17 being 20 minus 4 plus 1. Correct? So what we have calculated here is 20 factorial divided by 16 factorial. In other words, this is p of 20 comma 4, which is 20 factorial over 20 minus 4 factorial. So this is just the same calculation, but we did it 2 different ways. And this is really helpful for determining certain probabilities. So for instance, as an example, let's say we're collecting data from a survey, so survey of 45 students. 20 are B-STEM students. So 20 are B-STEM, meaning business, science, technology, engineering, or math. So, question, if we randomly select 3 in order, like 3 at random, in order, what is the probability that we select only B-STEM majors? So let's think about it this way. So our experiment is selecting 3 at random in order without replacement. So from a pool of 45 students, we're just talking about the sample space here. Then we pick 3 without replacement in order. This automatically tells us that we're looking at the number of possible permutations. So our sample space size is 45 factorial divided by 42 factorial, which is 45 times 44 times 43. We'll leave it at that for now. In our event A, remember that A is the event in which we only select from B-STEM majors. So, in fact, what we're doing then in A is we're collapsing that to 20 students. And from those, we select 3 without replacement in order. That means that's going to be 20, comma 3 for our permutation function, which means out of 20 factorial, we're going to reduce that to 17 factorial in the denominator, which will be 20 times 19 times 18. All told, our probability is going to be 20 times 19 times 18 all over 45 times 44 times 43, which is roughly 0.0803. So this is one way of using or finding this probability, thinking about it in terms of permutations. This actually, though, is very similar to what we've already done, in which we were talking about probability tree diagrams, where the selection without replacement means that the conditional probabilities still hold. So alternatively, we can think about it as probability of selecting only B-STEM students. So the probability of selecting the first one being B-STEM times the probability of selecting the second one being B-STEM, given that the first one was, times and so on. In other words, we're moving down the branch where if we're selecting B-STEM or not, we keep only selecting B-STEM. And each time we're reducing the number of possibilities because there's 20 B-STEM students out of the original 45. And then out of those, since we've already taken one out of the pool, now there's just 19 out of 44 left. And then there's 18 out of 43 left. And lo and behold, this actually does give us the exact same thing as what we calculated before, just in terms of these fractions. But it's the exact same answer. So this coincides with what we talked about in terms of the multiplication rule, and we have found two equally effective ways of finding that answer. One depending on the permutation principle, and the other depending on a probability tree diagram, which you may or may not want to fill out entirely. And in fact, sometimes it gets really unmanageable.